again for the physics show. We're going to do some funny stuff today. The main thing I want to introduce is something that I discovered quite accidentally a long time ago. This was in 1969 when the Super Bowl first came out. And we'll demonstrate it a number of ways. But before I do that, I might point out something I just noticed this morning on the New York Times, and that's on this particular little thing here. And if you'll click on this when you get to your browser, you'll get this little display here of American Institute of Physics. Actually, American Association of Physics Teachers, but that's part of the email. And there's some really cool stuff. It goes down to about the ground floor of the next lab place, and they're cool things. And one that kind of, well, you should be able to answer easily after we get done today is the, well, I don't know what the word whap is, but this is the whap baseball. This is Paul Hewitt, who's a famous improved teaching guy. And there's a little question there, 3 choices, multiple choice tests there that you should be able to pass easily after today. So let me just go quickly through what we need to do here today, and this is what it's a really crazy effect I'll show you right away, is modeled with some, as always, some idealization, the idea that you can play around with a thing and make it so that you get a good approximation to what actually is happening in this experiment. And then what we're going to do is we're just going to go through a completely, I think, very different way of doing physics, in elementary physics. So this is a demonstration that you should, I think, use in any physics class, but I'll go ahead here and just show you basically what it is. I just very quickly. This is actually an original Super Bowl. This is 1965 when they put them out, and that was an accident too. There's so many things in physics that are really cool that were discovered accidentally. Quantum mechanics is one of them. I think classical mechanics is too if you go way back. But the idea of this is a ball which, if you have a nice solid floor, which we don't, we have a rug, which cuts down on noise and all that, and it's a good thing to have, but when it comes to doing Super Bowl demonstrations, it's not quite as good. But I'll just go ahead and drop this thing and show you what it is I'm talking about. And that's not what I'm talking about. And I'll try it. Actually, what I'll do is I'll do the demonstration with a ball. That's what you would think would happen most of the time with this, and that's what I thought was going to happen when I discovered this accidentally. I was trying to do a problem that asked what happens if you grab a point on a rotating sphere and just hold it still. What does the sphere do? Obviously it wobbles around that, but just how much? I'll take this one right here and try to drop it on something that's pretty solid. That means I'm going to try to keep it from swinging and then let it go. That's the effect, okay? Now, on a solid floor, if you have a solid floor and you have a big lecture hall, you'll stick this in the ceiling. I mean, it's spectacular. Okay, it's also, as I point out on the, get this going here. For some reason it isn't even responding. That's weird. Let's see if we can get this guy fixed here, because we do need to keep up. With a big class like this, we need to keep the screen going here. I don't know what's happening to this.
Did you put your device receiver in the USB port?
Yes, I did.
Pop it.
I'm going to take it out and see if that makes a difference. Yes, it does.
It didn't hurt, but it looks so
and this is the wrong, yeah, here we go. See if I've got that. This is the device that we're talking about here. And there's a disclaimer. Okay. The thing is dangerous. Okay. I could have easily been half blind after this little experiment. What I was trying to do is, since the super ball grabs the floor and bounces back, in other words, it was equivalent to the problem of asking what happens if you stop a point. I stuck a pen in the ball, gave it a spin, dropped it, and the pen disappeared. I mean, it disappeared. I was already frustrated with this problem, but can you imagine how frustrated you are when you're dealing with what a 1-year-old is dealing with, an object permanence. Object permanence had failed. The ball, the super ball had thrown or sucked the pin in or done something. So I started swearing and cursing and kicking things, and my friend next door came in and said, "What's the matter, Bill? What's the matter? What's the matter?" And he says, "Why do you have a pin stuck in the ceiling?" And there it was. So that's the history of this genius discovery, right? There's an idiot playing with a pin in a Super Bowl. So we end up with this wonderful toy, a wonderful class project eventually a year later when I taught my first big class at USC, that's Southern California, University of Second Choice, or the University of Spoiled Children, is what it stands for. But anyway, I made the class more interesting with this, and also explained physics a little better. And we ended up with a paper in the American Journal of Physics with 23 authors. And at that time, it wasn't okay to have 23 authors. So they all had to go in the back, and it's called Class of William Harter as a title. So that we'll talk more about the history. There's a whole bunch of history of this bouncing ball business, some of which I'll mention maybe later on. But in any case, this is a site where this kind of thing is brought forward, so it's worth being part of that. If you're going to be in physics, you want to look at interesting things, this is where you get to do it most easily. Okay, now when we get done today, I hope we'll be able to see how this geometry that we've actually started right here, and we're going to do some more over on that board right there in the piece of graph paper that has the coordinates of 1 and 2 instead of 10, 20, 30 up to 100 is the one that you'll use today. And we'll be graphing again the Lagrangian function. We've already kind of done that. That's the ellipse. And we'll also talk about what's sort of the other way to do it. If you do it in momentum space, you get something called the Hamiltonian. And then there's something in between no one talks about, which I call the Lagrangian. And so these are all things that we'll cover in chapter 12 of Unit 1 in detail. And that will get you so you really understand what it is about the Lagrangian, Hamiltonian, and their illegitimate offspring, which is really powerful. We'll see that fairly shortly here in lecture on Monday. But that's what we're going to talk about today. So let's go ahead and get started. Remember, and this is what we did in the first lecture, is we simply asked what happens with this three-way collision in one dimension here for two extreme cases, one in which there is absolutely no friction and energy loss involved. We defined energy by doing this, kinetic energy that is. And the other case that we actually got first was the crunch, where you make one mass out of two and see what the velocity of that single mass is. What we didn't show is a picture of kind of a whimsical picture that I drew here of what you would call the center of mass. So the center of momentum and the center of mass are essentially the same point if you play your cards right. And this balance is going on all throughout the collision as it goes. And that's essentially another way to state the conservation of momentum that you were arguing about. You see, that balance is much deeper, you see, than that of the second axiom, which was the time reversal axiom, which is very much an idealization for classical collisions, but not quantum ones. But then there's another problem with the quantum ones, and that is that the uncertainty of the thing you call energy, that's frequency, could be quite large. and usually is. So, that's what we're going to make use of. And in particular, I want this homework problem done for a couple of cases, so that you really understand what the geometry of the Kabong ellipse versus the one that has less energy, and the one that you'll have a lot less energy in the third exercise that you do. But then, as you look in the center momentum frame, you should see this ellipse down to the smallest that it can be. That is, it will be within the boundaries that are associated with the time reversal transformations. The Galileo has that is, you just take everything you're doing and slide it 45 degrees down. That's equivalent to adding or subtracting a particular value of velocity to both of these quantities and anything else that's in the experiment. So these are all things we've already talked about, and maybe before I go on, I should make sure there aren't, if you have a burning question about this, maybe you want to ask it now, or maybe not. Let's go on and get on to the X2 here machine. This is another picture that's in the textbook that sort of emphasizes what happens as you could try different reference frames. Okay, so here it is. This is the thing, which we have lots of simulations for this thing, and you can, in this simulation, you can take some of the idealization away, particularly friction or gravity if you want to take it, but the thing is set up so that the object has no gravity, and you've just thrown the thing down, the thing being two balls on top of each other or next to each other in such a way that they both have the same velocity heading for the floor. Now, I have to admit that the idiot that discovered this, that's me, had no idea how this worked. I just figured, oh, these superballs are magic. They have shock waves in there. I don't know much about shock waves, but I know that they can throw things, maybe, and it's got to be shock waves, okay, or something, right? And I was not, until I got to USC, I figured I want to use this thing somehow. I had to figure out some way to do this. And that's what we're going to talk about very shortly here. But if I had a computer like this, it's obvious what happens. There, you see, this is so nice to have these things. So I'll just very quickly run the simulation here, I hope. There it goes. That's it. Now you say, wait a minute, those guys were separated, right? Do it again here. Reset t equals 0. Okay. Okay. They were separated, so let's do it again. Let's pause. So the deal here is this guy gets to turn around completely before it heads on into the second one, right? So theoretically it shouldn't work at all, but it does. That's something we'll hash out as we go through. About chapter 6, we're going to answer that question. I can give you a rough answer later on, but the basic idea is that the force function, the potential, things we're not mentioning at this beginning part of the classical mechanics, are very nonlinear. Okay, so anyway, when you resume this thing, it's a head-on collision, and boom, and it's straight all the way, just like the thing that we made yesterday for the collision of the two cars. Okay, so that's the thing I want to do, and then if you let it go, it does the thing we talked about last time. It just keeps happening over and over again, various collisions. Okay, so this particular case right here is very special, and that's what we're just going to deal with that, and maybe a couple more collisions today. And see, also, and this is the thing I really want to get across, is that when you do this geometrically, you get to see a whole bunch of things you might not have thought about. And that's another advantage of doing things geometrically. You get a road map, and then the road map says, hey, what's over here? okay, and you get new ideas, okay. So that's the commercial I just gave you for what we do here. Okay, so let's bring this one up to speed. See if there's anything here that I need to say in addition to what's already been said. I think we can wait. Liability disclaimer, gotta have that. And also, what was really neat about the USC experiment was I didn't intend to make it a lab project, but two of the dental majors that just like to build things came in just, you know, out of the blue, having built something like this that could drop a super ball absolutely without missing, like I usually do when I just am nervous and drop it, and then the thing goes off to the side. It could very easily have gone right like that, you see, in my first experiment. In any case, the idea was we were going to use two balls instead of a pen and a ball, simply because of the safety feature, difference in safety. But anyway, the idea was to have this thing spring out of the way, just fall out of the way, so that the ball could, or the other ball, the second ball, the pen, could go to whatever height it would do. So that's another idealization that we're taking here, you see. Remember, this is a course that starts with nothing and uses practically nothing to get us going here. What we're saying is that the forces that are, and we aren't talking about forces, but I can mention them, the forces here are really large compared to the force of the gravity, the weight of the balls, okay? So we're just imagining that we're on the moon, or else we're just out in space, and we throw this thing at something solid, and it comes back at us. That will be our experiment. Later on, we'll talk about all of the stuff that has to do with it falling, and we'll use more balls, get bigger bangs, okay? And that is something for a later chapter. Chapter 8 is where the big number of things increases in our discussion. So what we need to do, and I'll bring this one up to this one, and let's see if I've got, oh, I haven't even gotten this one to play yet, so let's get her playing here. This is the, I hope this is this is the Firefox thing. I've got to get out of here.
Yeah, that one was running.
I keep forgetting where we are in the IT space here. Okay, let's keep going to here. Now, one of the things that, you know, it's always true that something can be done really simply, and then you come and say, oh, but how do I understand the fact that if I just drop a ball on the floor, it comes in at a velocity which is pretty well matched on the way out, and if it was really perfect, it would be 100%, it'd be 100% coefficient of restitution, okay, which is, the super balls are famous for having the high coefficient of restitution. Now, I mentioned it was an accident for them too. This is Wemo Manufacturing in San Gabriel, California, and what they did was they were trying to make some kind of rubber that would work for I don't know, they just invented the hula hoop, and they were trying for something that was kind of like that. And they made a couple of things, and then they cooked it, and I think they were just making balls at first, and they didn't like what they got. It was this weird looking black stuff like what you got right here. So they threw it in the dumpster, and went boing, 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 and came back out. And they said, oh my gosh, we can make money. We call it flubber or something like that, right? And that's when the Super Bowl was put on the market, within a year of that thing. Again, totally accidental discovery. And what they'd done is they fixed it so that the side chains on the polymer that makes up this kind of rubber were locked in. They were more locked in by just the right kind of stuff they were doing. And as a result, it doesn't waste very much energy when it compresses. It bounces back with pretty high coefficient of restitution. Now, if you have really good steel, and you have a really good steel anvil that's, say, hundreds of pounds, and you drop a ball bearing on that, the coefficient of restitution can be very close to 98, 99%. So steel is better than Super Ball. But Super Ball has the advantage of having that coefficient of restitution even when it falls on something that bends a little bit like linoleum or you know, any kind of floor. So be aware of that. And anyway, that first bounce is the thing. Let's get it drawn on our graph here. And the graph that I'm looking at here is, instead of having the SUV, the big guy, be our horizontal axis, I'll just put, and this, you should make a notation of this for your axis, your x-axis of that graph. And we're not going to go much outside of 1 here for anything. We'll make notes and stuff. But most of these things that are going to happen right in here. So let's just call this the ball axis. V super ball. Don't bother writing super. And then the pen, the thing that flies up and tries to put your eye out, is this axis right here. That's the velocity of the pen. Before, after, all of the kind of stuff that we did in the first lecture is going to happen here, but we're going to try different mass ratios and all that kind of stuff. But anyway, the actual starting point for this particular experiment, we're going to take it to be right here. This is the real initial, the zero, the absolute zero initial. And that's where you have -1. I didn't bother to write the -1 here, but it's on the graph paper you have. Here's +1 over here. There's +1, there's a -1. But this is -1 for both velocities. So we're going to start off right here with both of them at -1. So they're both coming down together to be hit by the earth, as it were. They're going to hit the earth. Okay. Well, they're going to hit in such a way that the first one gets to change its velocity completely before the actual collision between the big ball and the little pin ball occurs. M1, M2, if you were being less prosaic. So that's what we're working with here. And if I can find my magnetic ruler, oh, thank you. There it is, hiding in the, right in front of me. Basically, what we're going to be doing is, first of all, drawing that initial thing. So I'll pick some exotic color, like, I don't know what's the name of that color. It's not PHYS. That's a purpley color, right? But anyway, there we go. And you might put a few indications of where the motion was when this really fast collision occurs. But whatever it is, it ends up exactly here. Well, almost exactly. That's assuming that the thing that it hit, namely Mother Earth, doesn't recoil at all. And that's what all of this is about. Okay, so this is, this is something you can easily ignore. But I don't like to ignore things. I'd like to point out that really what we're talking about here is a collision between, say, a super ball of, let's call it unit mass, and something with 100 times that. And then the square root of 100 is 10. So I get an ellipse with a 10-to-1 ratio. That's, if I make it any bigger, I can't draw it for you, so that's what I picked, just as an illustration of what we're really dealing with. So we're dealing with a collision that goes from one part of the ellipse to another with a line that has a slope of the mass ratio of 1 to 100. So this is a case where the mass ratio was 1 to 100. What we're drawing here is a case of where the mass is 1 to roughly 6 times 10 to the 24th out of the number of kilograms in the Earth. So as I said, I could just draw this line, no one would argue, but I'd like to be picky, right? And point out, well, even that isn't quite right, but we'll worry about that later, and it'll be a diagram that's very long ellipse. Okay? So everyone knows that if this thing is a perfect bouncer, it's going to go from minus to plus, and that's our whole story right here. And then it's the collision between the two that have a different mass, and that's what we know how to do with geometry like this. Okay, what sort of mass ratios do we have? It's up for grabs, okay, and that's what's cool about geometry is I can stick this ruler starting here, and to change the mass ratio, I just go like that, right? That's changing the mass ratio, okay? So I think what I start with on this particular case is, and I'm going to keep these two screens as much in concert as I can if we get done discussing that kind of stuff, okay? Then this bang 1, and when you're reading the text, there are little subscripts here. The first bang consists of the mass we call M0. That's the plate upon which this thing is going to hit when we do the experiment that I just did again. And then the ball, 70 grams, that's the typical mass of superblocks, is 69 point something. And then I get a 10 gram pen. That's typical for a Lindy pen that had a nice brass thing that I could stick in a superball. So we're talking about a 7-to-1 ratio there. And so what I have to do is put a line up here that has a slope of minus 7 to 1. Right? Just like we did for the ratio of 4 for the SUV and the VW in the first lecture. So without the ruler, I'm going to take the ruler off for just a minute here. It's time to make something of slope 7 that is minus 7. It's going to be pointing down. So I'm going to start here, and I'm going to go minus 1 of my smaller squares here. You pick whatever square you want. A pretty small one if the graph paper is kind enough, and I think it is. And then you just go minus 1 and then up, plus 1, 2, 3, 4, 5, 6, 7. And make a big dot that you can see. Now to make it easy for you to get the line that's a slope, we need more leverage. So I'm going to do it again. I'm going to go over here, minus 1, and then I'm going to count again, 7. 1, 2, 3, 4, 5, 6, 7. Draw another dot. And this momentum line that's going to start here, it better go through those 3 points just to make really sure that you've got a precise measure. Go minus 1 again, and then 7. 1, 2, 3, 4, 5, 6, and 7. Okay, so the ruler should go through all of those points, or I should say the edge of it should do that. And then you slide it over just enough so that whatever pen or pencil you're using can make a line that really goes through all 6 of those points. And it looks like I need to slide it over just a tiny bit there. And I've got 3 dots that are right where I want them. And so the momentum line you can now draw. Now there's one other line that we need to have in order to figure out where this collision is going to wind up. So I'm going to set the ruler aside here for a minute and point out this guy right here. Now in the graphs that are on the screen here, I've got a dashed line already in place, and you can see that right there. Let's keep going here. This is what we want. We want to find that point right there, the center momentum point. Now, one of the things I think we, if any, make sure everybody has a piece of graph. And also, we do need a compass for this one because we're doing the elastic case. So we've got a couple more compasses here. If you don't have one, here's a high class one. Anybody need it?
The extra, I'll look for some more. Have you got some more on that end?
Some more graph paper?
Yeah. Well, this might not be the right one. I'm not certain.
That's the one for the SUV, and because it's got big numbers.
Okay, she was correct in that.
Let me see if
It ended up on this side. Yes, yeah, it ended up over.
I can always make more.
Well, you can
Who is
create.
missing out? Graph papers. This is something I want to make sure. I got some spares, I think.
Yeah, I mean, I'm trying to do this as implemented as possible on that.
Thought I did. Here's some. Who needed it?
Yeah.
Anybody else? Okay. All right. So let's get that. Now I use blue for that. Since it's on the screen red, I'm going to go run for some red chalk here and draw the COM line, center of momentum line, the one that you put your compass point on to get any mass ratio that we do here. So I'm just putting the thing here so it goes through the cross points at 45 degrees. So this is the line that we work with our compass point. And there's the point right there that I'm interested in for this particular mass ratio. And then I'll go ahead and run it all the way up here just for the sake of completeness. Okay. So if the super ball and the pen had super glue on them, say somebody snuck in before the thing and put some super glue on to ruin the experiment for the professor, he would end up here, right? But no, we're going to end up a lot higher, and that's where the compass comes in. So, looking for my compass.
You have one below there and then one on your next to your cleaner.
I think maybe this one is the more robust of the two, so I'll use that. Thank you, TC. Okay, so what I've got to do here is draw one circle. I don't have to draw the whole thing. I could just go and mark the point up here, but just to indicate and make it look like the diagram we did the last time, I'll go ahead here and see if I'm going through that point pretty well, and it looks good. And I'll just bring this thing around. Hopefully the compass will maintain its radius if I don't flinch. And then I'm going to be going through right about there. And just like yesterday, I can see I'm just a little bit low. That's because I know the answer, but probably not something you'll notice. So the question is, what speed in these units, that's the unit velocity that we gave the thing to do the collision, to hit the floor, and then the other one hit each other. What velocity will we be making? Now, our center momentum velocity right here, I'll go ahead and draw the engineer symbol for that. Center. But up here is what we're looking for. That's the answer right there. Okay. Well, if you look on your graph, you can read this very easily. On my graph, I have units here that are 0.2, 0.4, 0.6, 0.8. So right between 0.4 and 0.6 is the speed of the ball. The ball originally had a unit velocity. Now that has been reduced to about a half. That's what I'm looking at this point right here. But the pen itself is about 2.5. Okay? So this gives you some feeling for when this really works, and you sometime in the future are on a stage at a large lecture hall. Very easily this is going to reach the ceiling, right? If that were completely right. Now obviously there's some losses, but it's not significant. At least not when you do the experiment. Nobody's going to be able to read the thing. So anyway, we're seeing there a 2.5 that's squared to 6 1/4, right? Okay, that's the kind of ratio we're talking about. What sort of ratio in height do we get? For example, if we had this thing come out, as we're going to very shortly here, by changing the mass ratio, come out to there, okay, with twice the velocity, how much does that amount to in height? You see, that's a good question to think of. Okay, well, as I said, this is a slide rule for figuring out all possibilities, right? So we got to work it. Let's go ahead on this graph here. See if there's anything I need to say about these two things. The first bang, then the second bang. This is all in the textbook, and it's got this funny notation that uses a subscript to indicate which mass. In this case, Earth is 0, 1, and then later on, number 2 is the pin mass. So the independent bounce model is what we're using here, and there's the result right there, half 2.5. Okay. So the second bang is this thing. We came along this line, and then we go up this line right here. Little arrows to indicate. So the momentum of each of these masses is being conserved at first, 0 and -1, and then boom, it's not conserved for just a millisecond or so, and then it's going to sit here for a while and fly away. No gravity. We're pretending the gravity is not there, so these guys don't go anywhere until there's another collision. And the idea is that we would like to go ahead and put a ceiling. And we actually had that in this experiment. It was a concrete building. We had a concrete ceiling and a concrete floor. So we play all kinds of games, but it's hard to measure things on that second bounce. But nevertheless, when I'm doing a computer thing here, we could do that. So let's go ahead here, and I'm going to ask, is there a way to optimize this in terms of the ability to throw things of different mass? What is sort of what's the whole gestalt look like here? And so what I'd like you to do is make a couple more lines with different mass ratios. We'll start with the case of a very small mass coming to us. Let's say, and this time I won't quantify it at all, and you don't have to either. Just put your ruler down on the initial point there and go, right about there. Okay? So I'm going to draw another, and I've got to make sure I let the chalk make a line that goes through this point, and then everything else will be determined. So the next case that I'm considering here, it's like a mass ratio of about 10 or so. It's a slope of -10 for the momentum line. Okay? And then my center point is right here. Okay? So once you find that, it's compass time. And we'll draw another circle to find the final velocity. And that means resetting the compass. This is a bigger circle. And I have to make sure I keep the point on there. So whatever point this is, we just picked it randomly. I am going to, that's the trouble with blackboards, they're slippery. You can just make yours go into the paper so you don't have to worry about that. And I have to come around and I have to hit that line right there. Okay? So wow, I'm getting almost 3 for a final velocity here. Okay. Now, let's take a really extreme case where I have just a little particle of dust for the pen. Okay, something milligram, all right? So we're talking about a slope of 1,000, or make it more, 2,000. You might as well make it infinity just to see what that result is, right? So here's the limit of throw for this super ball experiment. Infinite, right? And I know the result from this one. I don't need to get my compass out. I've got 2 units here. I've got 2 more to get to the point that I'll get when I finished with the infinite collision. So this is the M2 approach 0 as M1 is whatever it is. M1 equal, we're talking 70 grams, so we might as well just let that be the actual mass. But this is M2 approach 0. This is basically the infinite slope of the momentum line. And it's the absolute limit 3, okay, for the throw. Okay. Now, looking at the geometry, I see 3 points there kind of determining a line. I mean, this is an example of geometry giving you a clue that something's up. So for example, if I take, and we could just check this by doing a 4th point over here somewhere, and I'm just being, random with my choice. That's the thing you can do geometrically, as you would on a simulation of a computer. Okay, I could do a 4-to-1 ratio right here, as opposed to the 7-to-1, and I would have a line that went over like this. Okay, and then when I get my compass out for that one, again, I have some velocity that will be on that line, and much lower than the one that we did first. Okay, so what I do here is set the center point with the compass point and draw one more circle. And everything slipped as I moved to get out of the way here. Make sure I'm still kosher here. So here will be yet another final velocity point for that thing that just comes right about there. Okay. Right about there. Now you put a straight edge on that, and it's pretty clear what's going to happen if I were to pick a mass ratio of 3-to-1. Okay? And that's the optimum one. That is really something, because that one is leaving no energy behind on the ball. The driver of the thing gets to exhaust all of its energy now. So I just go there and draw that particular slope. a 3-to-1 mass ratio as opposed to a 4-to-1, which is next door, ends me up right there. Okay? With no velocity left for Mr. Ball. Okay? That's kind of cool. That's a prediction of something we can test, right? So, what we're looking at is a very famous geometrical theorem here. When you have a bunch of lines with different slope through a point, that set of lines is called a pencil. Pretty obvious name. It looks like an old-fashioned pencil where you sharpen it with a knife, right? You get all these little facets on the end of the pencil, right? So a pencil of lines. And of course, what they really are thinking about, of course, is not just a pencil, but a whole fan, which, you know, goes all the way around. Those are all possible lines, and there's interesting collisions experiments. But this is kind of the limit for us, because the next thing that's going to happen is it's going to give us a situation where the ball has been sent down by the collision, negatively. That's interesting. We're going to study that in great detail later. But this is kind of a neat limit. Okay? Well, once I figured that that was the case, I just didn't wait to try it. And what I did was I went to the shop and made a brass pencil. Doesn't write very well, but it's really heavy. Okay, it's 20 grams. Okay, and this Super Ball, these are the cheapies that came out later. If I can look at this thing in a, I don't know if I've got. You know what? I don't think this is the original one. I'm wondering if I've lost the original one. It had 60 grams. That's, well, let's just pretend it's 60 grams, see what happens. I've got to get the thing to stick in there. I didn't check this before class. I saw a blue ball and I figured that was the one, but my gosh, I think I have lost our classic thing. I'm going to go ahead and use this particular one, which is about 65. It's slightly smaller than the other ones. Anyway, let's just see what happens with this big mass compared to the 10-gram mass. I'll drop it right in the corner there, so it's pretty solid right there. And we'll see what happens. Now, yeah, shield yourself because the pen might go somewhat, but you can see it doesn't go as fast as the other one does. It's got a little bit of a bounce, but the thing that I can't show you is the beautiful, really 20-gram ball, which just sits there after the collision. And that's, as we're going to see later, thank you, as we're going to see later, that's really quite remarkable that this works out. Because remember, we are assuming independent collisions. And when you've got the pen stuck in the ball, like we have been doing all of the experiments that are in this paper, they don't look independent. But just to give you an idea, and we'll prove this in more quantitative ways later, what we're talking about is the force versus distance of this force versus this number right here, the depth in which the ball gets crushed, that is the depth at which its surface as it would have been if it didn't get crushed, has gone below the 0 point. So you write a force versus a distance. Well, Hooke's law, if for F equal K D is just a straight line, and K is 1, it's a line at about 45 degrees like I've drawn, but if you talk about something that has a power to it, say F equal K D squared, okay, then what you'd see is something like this, okay. And if K was 1, they would meet at 1, 1, okay. And then next after that, maybe, as you get freer and freer with exponents, you go F equal K D cubed, okay. Well, that gives you something that goes like this, and then scoots up. I'm exaggerating, obviously. The point is, as I go to D equal 4, 5, 6, 7, 8, I get closer and closer to something that just stays really flat, and then says, "Oh my gosh, I should have gone up," and goes, straight up. You can work on your graphing calculator and see all the curves that have different power laws, right? But all of the power laws have this flat region. That's equivalent to a gap. That's why these experiments that we were doing didn't require solving differential equations, which is really what you have to do to take care of the mechanics of the thing in very great detail. Nevertheless, this project got very famous at USC. It was put on NBC News, Ray Duncan Reports, which everyone was watching, and he's a really excellent comedic newscaster. And he came down and photographed a day at the project ball, which was in room 69 of the old physics building. It was about to be torn down, I think. It's very old, but they let us take it over and make a lab out of it for some time. And I'll tell you the stories about that happened in that much later. But in any case, the newsworthiness caused the engineering department, or a subset of the engineering department, to say, "Hey, we want to get part of this." And they went and measured the force, the actual force as a function of D, using a very expensive instrument that they could read off. They also let us use their analog computers. Remember, the digital computers are not the kind of things that we have so much of now, where we could program the coupling, and we were interested in doing more balls, so we knew that the independent collision model needed to be given some, more precision. And after we get all done with all that fancy stuff, and compared it to the curves that we were getting from the drop tower, it was way off. It was way off. And this was the, it's one of those things that happens in science. As you figure, oh yeah, I'm pretty good, I know this stuff, let's go further, let's go further. All of a sudden, oh crap, it's not working. And here I was, professor, supposed to be smart and know what the hell's going on, and it was clear that I didn't, at least to the more sophisticated of the one, but they were all curious too, like, what the heck is going? So, I said, we got to do something. So I said, hey, why don't we call up Whammo, and maybe talk about this as a toy or something, we can make money. And, they just forgot about the fact that we were screwing up. And we went down to Whammo Manufacturing. And I talked to a guy, he says, yeah, it sounds like a really good idea. Why don't you guys, we'll give you a tour of the plant, and you come and we'll talk about this. And we finally, it took a while to get enough cars to go down to San Gabriel. I think 20 of the 23 people went on this little tour. And when we get there, the day we picked, and I didn't realize this, was the day that they do their alpha wave sessions. That is, the inventors do. They make themselves more creative. Okay, and only get to talk to a lawyer. And we said, what's the chance of this, that you might want to make a toy out of this? And he says, it would really be dangerous. After he saw the thing stick in the ceiling, he didn't imagine a lawsuit because people are sticking in their eye, right? And he says, well, I'm sorry, guys, but still, you came all the way down here. Well, let me give you something. They had a whole bunch of Super Balls, some of them as big as this, and they had all sorts of other things that were made out of Super Ball, mainly a whole bunch of balls, and we'd torn all ours up and running out of money replacing them. So we were happy to take a big box of balls back to the lab. And And it was also, the other thing that had happened was we'd been kicked out of the lab because they were going to try to repaint this particular basement and make some kind of lab out for a while. And so we were kicked out for a week, and we went back to the lab to just put the balls there, and the kids were saying, "Hey, great, let's see how they dumped this box out, and all the balls went running around." And of course they got in the paint, and then they left little spots on the floor. And that's when I realized I usually have to think a long time to get something that's really a eureka, but this one just came instantly. I knew what was wrong with it. All this fancy computing that we've been doing, and why it was giving us wrong numbers, and what it is about nonlinearity that you really have to take account of. And what I realized was that we could measure the adiabatic force curve by dropping the super ball and making a spot with it. And as the spot got bigger, we could tell how far we'd gone in, and the height of the bounce would tell us the force energy, the potential energy really, and then the force occurred. You see, long story short is that we did that, and the paper was worth printing. That is, it didn't fit the results that we've been doing, plus it let us get some information on this one. We'll talk about it later. But that was the key to this, was that we had been playing with a curve here that is very flat and very steep, and it's like super putty, you know, that kind of stuff that's very milky very soft when you don't push it fast. But when you push it fast, it bounces really, as well as a super ball. And if you really throw it, it shatters. And that's what super balls do too. We found that out very, very early in this game. Okay. So that's half of the super ball story, which we'll tell the other half later on. In the meantime, I want you to notice that this curve goes further, and it also turns thing negatively. And this is a picture of what we've just been talking about. There's the say one, but as it goes further, okay, you start getting negative values. That is, the pen becomes heavy enough compared to the ball that it sends it back toward the floor. So that's what I want to look at for the rest of this particular lecture. And also, and this is something that maybe now I'll skip, but a thing that we'll be asking you to do on some problem is to integrate the velocity curves geometrically. No calculus, just a simple arithmetic of this. And that is that whenever you have a point for a particular mass, like m1 here at a velocity of +1, okay, this particular point, that is this arrow here, means that m1 is somewhere on the space-time plot, and also in the space-space plot. But in the space-time plot particularly, if the velocity is 1, then there's a line of slope 1 indicating where it's going, and which one of those lines with slope 1 do you pick? And that's called picking the integration constant. That's the big deal in mechanics that we will run into plenty of times as we go forward with all of this. So that idea is really important. And until you specify that, you can't say what's going on over in the space-time or in space-space. We also need to plot the rest of our phase space, that is x1 versus x2. We've got v1 versus v2. That's given us lots of information, but now we've got to get the whole story right, and that's what I'll ask you to be doing. Now here's a couple of examples of that. Here we start with these two objects, the big ball and a little pin on top. We're going to start them out at just arbitrarily 1 and 3 height, and having a slope of -1, that's what we assumed. We started with a velocity of -1 for both of them. Again, ignoring all of the gravity that would be involved in an actual experiment in this room. We're just thinking of the last instant before the collision and afterwards in our dealings here. But in any case, that's what you have to do in order to see what's going to happen. Now, this is going to tell us that this ball is going to bounce right there, and if it's a perfect bounce, it's going to come up like that, and it's going to run into the pen about there, you see. So that's what we need to take account of. It's going to bounce off like that, and then keep going. Each of them are going to keep going. So the result will be that you'll find a collision right at that particular height between the two. And then that's when you use our velocity geometry to find the next point. Well, we've already done that. We've considered the case where they're 1 and -1, and that's the start of this thing. And then whatever mass ratio, that's the end of it. So that's the way you calculate these things as it go through a whole sequence of collisions. So this is going to keep this thing here. We've got to figure out what the velocities are from that. That's what this thing that we just did is. That then gives you this line and this line right here. A half slope and a 2.5 slope. That is our very first result right here, which I'll just emphasize by putting a little velocity coordinates. The V1, that's the ball, V has been reduced to 0.5, and the poor little pin has been sent to 2.5 in velocity. Okay, so they're going to continue, and now if you have a ceiling, and that's what really makes this a whole interesting problem, because it keeps going then, and it'll just fly off forever, or fly off and fall. That's something you can simulate later on as well. Then you have to say, well, where's the ceiling? And that top guy is going to hit it. Meanwhile, the ball is going to continue its merry way until it runs on into the little ball, the ball that you call pen, right at that point, and you have another collision to look at, and so forth. So this is, you see, letting you do the geometry of some pretty complicated behaviors, which of course we can do simulating very easily, but there's no calculus involved. It's just simple geometry all the way through, with the idealizations, of course, that we've assumed here. Okay, so when you do this, of course, you're going to get a bunch of collisions over and over again. And what I'd like to look at before we quit here today is some pretty extreme ones, and then we'll go into more about that later on in the next lecture. But I already showed you a little bit of this in the first lecture. Now we're getting more quantitative about that. And here's the other thing that you can do with this, and that is every time you have one of these funny vectors that have components of one particle versus another, like our Vn and our Vfin, we've got the same thing going over here. We have, first of all, the very easily found velocities down here, but then the velocity that's associated with this particular 5.5 and 2.5, that's V second bang right there. Then you make a little parallelogram, or whatever you want to do, but you draw that vector over here from the point of collision, and that's the way you can follow in the space volume the time behavior of these objects. Now all of this is built into the simulations, the bounce it program that I originally wrote in Fortran, and now it's been put into by TC HTML5, so you can run on a browser. You don't have to buy a Mac to do this. But in any case, we start making collisions back and forth. Now, what's really interesting about all of this is, and this is something we haven't done yet, and that is, here's an example of something that's really a simple mechanics problem, but it's a horrendous quantum mechanics problem. And that's what we're supposed to be good at here, is we're supposed to be able to do semi-classical physics. And we have not yet been successful at figuring. I mean, first of all, this collision line here is easily crossed. Easily crossed, okay, in quantum mechanics. For us, it's not. You have to make the pen go through the ball. Okay, so I'd like to show a little bit of that later on. In any case, this is the kind of graph paper for the next exercise set that will be coming out Monday, and I'll be asking you to do a couple of the bounces in space as well as space-time. So that is an interesting thing. Now let's just take a look at what the simulation is. This is kind of neat, and this was something that will set up another whole area that we can introduce in a, I would say, inventive way. This one is a case where I have 49-to-1 ratio. 49 is 7 squared, so that helps in a little bit of the geometry plotting. But let's just take a look at that particular...
You missed the link.
I missed the link. Yeah, let's go back and get it. You got to get the little thing giving you the finger there. There it is, right?
Which finger is it?
Yeah, it's this finger, not the other one. But anyway, if you click it, then you'll actually get the simulation. Let's see if that works out here. Yes, here we go. So here we are talking about 49-to-1, and that's a heck of a throw, okay? And you can see from the slope that it's pretty high. And as you and this thing is set to pause. You undo that from the control panel so that I can stop and talk about what just happened. And as soon as you resume, of course, it's going to continue with more collisions. Now what's sort of neat is what we're going to do later is we're going to model the potential energy as the energy of this little guy, and the potential would be causing that curve, and it's not a curve, it's a bunch of straight lines, but it, if I make it a smaller, smaller mass, this becomes smoother and smoother until you have kind of what we think about as a force potential field. And then it happens again, and it's off screen there. You can make the screen time a lot longer. Now the other thing about this, and I'm going to just pause this right away and go quickly back to the lecture and pick up the other possibility. This is the time plot here. The V1, V2 plot is, of course, the one we're using for our geometry from the very beginning. And this is a picture of that. Okay, so that's the first shot, okay? And that was what I started talking about at the very beginning of this lecture, very narrow ellipse, right? But this is only, you're only talking 49-to-1. How about, hundreds to 1 or thousands to 1, okay? This ellipse keeps getting skinnier and skinnier, and the geometry gets to be more and more difficult. We've got to fix that. That's what we're going to be doing in the next few lectures that come up here. But anyway, when I resume this, it should go through the dance of filling the ellipse. There's something going this way and something going this way. We're just about at the tip of it right there, and the ball has turned around. We just passed the plus to minus ratio, velocity for the number 1 ball, okay? And then we started all over again, more or less. Now we start off very, very close to the 45-degree line. They're almost equal, okay? Now we're going to be starting off very close to where we were when we got our first collision, right? So this particular one, this is 49 to 1, is not being ergodic. Remember when I said ergodic is where you fill all the space that's allowed by your constraints of momentum and energy? This one doesn't seem to be doing that very well, though it seems to sort of be doing it. See these extra numbers showing there? Well, we're going to have to figure out a way to discuss how collisions like this occur. How do I analyze what's going to happen after many collisions? And that's the advantage of looking at this geometrically. One of many, I think. Okay. Now, any questions? This has been I've been doing all the talking, and you're very good at asking questions. Anything?
I guess I'm more. You can see that nice square there. Is it gonna like keep slowly building up
Well,
over like a really long time?
we'll try it. Yeah, I mean, all of this stuff is right at your fingertips now. Just go to the lecture and click what I clicked on, but you can also go to the original source of the apps and tear into the thing. It won't hurt for us just to take a few minutes, maybe. I'm going to pause this and notice there's a whole control panel here, okay? And of course, if you want to raise that, you're in big trouble right away. But putting a little acceleration, it doesn't hurt, okay? And also, the collision, friction. Okay, that's something we will talk about that just to see some of the weird things that result from that. So you can pick all these different plots, and I think this thing is, I'm looking at about half of this control panel here.
There's a lot more down
There's
there.
a lot more below there that
Scenario-
you can play with.
Preset scenarios too, so you don't have to worry about the controls.
Yeah.
You just push a button.
Let's see where, if I can just raise the thing up, that's what I should be doing here. Now the mass ratio, gotta remember where that is.
More towards the middle.
It's sort of in the middle right there. It's the draw first vectors, positive left down. I get lost on this
Well,
thing. I
it's
don't use it a lot.
It's a small projection screen, and he's got it slaved to it. Your more modern machines, you'll be able to play with it just like a web browser.
Yeah. Oh, here's the gap. How much of a gap do you give this thing? That's going to be something we'll discuss later on. Here is the mass right here. I've got M2 at 1, and then I've got 4.9 times 10 to the first, which makes 49, okay? It doesn't hurt to crank that up. In fact, one of the ways I can crank it up is just go like this. Now the poor little ball's going to get crushed. Let's go ahead and run that one. That should be interesting. There's the monster.
Started off inside the big ball.
I mean, this is ridiculous. We're going to push this thing. You'll see that the energy isn't being conserved when this thing. Poor
Crunch.
thing. Oh. And finally, he gets him going the other way. Right. So that's that. And to do this, let's pause just for a moment here. And let me go over to the other plot. That's the, instead of plotting V1 versus V2, we could do momentum. That would do
It's set up a little higher. A type of second. A little more towards your right. Your
to
left,
my
I'm
right?
sorry. Your left.
To my left.
Right there where it says blue.
Oh.
Type of second plot. Right at the top.
Okay.
There's how you switch your plots.
Type of plot. Oh, yes.
Yeah.
Yes, yes,
See,
yes.
it's folded. When we looked at it earlier, it was...
Yeah. Here is the time plots. That's probably the one that would make the sense that we've been using, right? Let's see
That's where you had it.
how that one works out. Now here's where I'm going to pause this again because I need to give it more time.
You might build a mouse.
Let's
Reel
give
it.
it more
that you didn't like.
time scale, right? There's a time scale. T max, right? Let's get that out. 30s. That should be enough for this one. Yeah.
Should be
Let's see
pretty
how
much.
that goes with this business here. Well, this is a real nice computer game, right? So here comes Monster, 490,000 grams, all coming there, beating the heck out of that little guy. Actually, the energy's holding not too badly,
It's not shredding.
and down it goes. Now you can see this is a very smooth curve. This is the potential energy is being, kinetic energy is being shown to make a potential. And this time it gets really close. It's a lot more, got a little higher than that one. So this is something we're going to study as well later on. What we'll have, if you want to make a harmonic oscillator, you put balls on both sides, little balls on both sides, and then your trajectory is cosine curve in the limit, right? It's not exactly, of course, it's very complicated, very chaotic actually. Anyway, it's this kind of thing that I think makes mechanics fun. And boy, it sure helps to have a computer. Because so much of mechanics is uncalculable. It doesn't fit to any of the algebraic numbers that we know, things that we know about. And your research, of course. And by the way, that's something else I should have linked, is there's a Mathematica course that's being given. Mathematica is free for you. How many people have Mathematica right now? 1, 2, 3. You raise your hand. 4. Yeah. Far superior, particularly for higher mathematics, than MathCAD. But MathCAD is more accessible. You really should have both. You go quickly to MathCAD for something simple, but if you want to do complicated things, they're not too great on graphics. The graphing calculator by Ron Abitzer is absolutely wonderful. It's fast, and you can make just about any function you want. Beautiful things. Mathematics is still a little slow because what's the name of the guy that started that? Wolfman. Wolfman is very algebraic. So mathematics is very powerful doing calculus and algebra, all kinds of topological things. But it's always been bad on graphics. They're only now they've got a whole division that's going to fix that. But we have a course for it on campus, free, and of course Mathematica is free. It's $450 for somebody off campus, but
I was going to ask.
it's nothing. You can get it. Just put it on your computer and you're off to the races. And I really recommend all of these programs for any of the courses that you take in this department. But certainly MathCAD and Mathematica are good for mechanics.
They've matured a lot over the last decade, the last few years.
I mean, it's and they have all kinds of contests and things like that. You can discover something weird. You publish it. You publish it on the Mathematica journal. Just send it in, and they look at it and say, "Yeah, that's kind of interesting." On it goes, and then you can update it later. So it's a new way to learn, new way to make contacts with people that are interested in the same things. It's a social media almost. Yeah.
Speaking of, let's give a shout out to Skander. I'm not quite sure where he's at, but we have already got a compliment on our class from
Good.
Monday. Online.
We can certainly use that because it's weird. We're doing weird, and I hope you enjoy being weird. Okay, we'll